prove this BFS theorem. And so if you recall, what the BFS theorem said was that when BFS terminates, then visited is true if and only if there is a path from S to V in G, that if S is connected to V. Then there was a statement on the predecessor. The predecessor is null if and only if V is equal to S or V is not connected to S. And then the third most important statement is that for V connected to S, that if you keep following the predecessors, you end up with the shortest path. Right? So these were the three statements that are part of the BFS theorem. And so what we did last time was we started proving the first one. What I'll do is I'll try to wrap that up really quickly. The second one, it turns out, is actually a pretty direct consequence of the first one. So I'll say it because you see, if V is connected to S, then visited V is true, right? And so what are the vertices that are visited? That's exactly the ones that are connected. So you know, and when something is visited, unless it's S, it has a predecessor, right? So every visited vertex other than S has a predecessor. And so that's all you need for the second part. And the third part, we'll sort of go over how to prove that. Now, the main tool that you need in proving that is actually this more complicated statement called the loop invariant. And so the loop invariant says certain things about what the queue looks like and what vertices that have been dequeued and not visited look like. The proof of this is more complicated and will be your first homework. So, second homework, sorry. The next homework that I'm going to release, hopefully today, is going to tell you how to prove this. So I'll break it down into various parts. And it's almost like a one-page document. So you read through it, it gives you the overall structure, then it says, okay, so you need to do this to prove the first part, the second part, so on and so forth. So once you do that, once you do the second homework, I think it'll be fairly clear why the statement is true. And so what I want to do is then just spend a few minutes, or maybe more than just a few minutes, explaining how the loop invariant implies the BFS theorem. So just to be clear, the way it works is we will assume that this is true, and assuming this and only this, we have to prove the BFS theorem. To prove that this is true, there is another sequence of arguments, and that is given in the second homework. Does that make sense overall how the proof structure grows? Right? So it really is very logical in that you cannot assume something that you have not proven. Right? So you have to go through the sequence to make the argument. Okay? And so my hope is that once you do the first homework and the second homework, which is the programming homework and this other more mathematical homework, you will have a very good understanding of how BFS works. Both sort of in practice because you've done the implementations and you use it, and also in theory. Okay? And I think once you have that, you'll have a much better picture of BFS than you may have had before. Right, any questions? Yeah.
Someone asked for the first homework how doing, I think it was doing BFS from a source node and doing BFS for the whole graph, like what's the difference between it? Because
I will explain that once I do this.
Okay, sure.
Yeah. So that would actually be once I finish the discussion of the BFS theorem, I will get into that. Yeah, good question. So if I don't, please remind me. Please remind me. All right. So let me just make sure I have everything I need. Okay. So just to sort of quickly go over this. So now we said the BFS theorem, assuming the loop invariant, right? So we're going to prove that. So we have three statements to prove, right? So we have statement 1, 2, and 3. So there are going to be three parts of the proof, and each of these there's an if and only if, right, in the first and second part. So that's actually two statements in of itself, right? So you have to say, if visited is true, then there is a path from S to V. If there is a path from S to V, then visited is true. So you have to argue both these sides. So in the first part, we said if visited is true, there is a path from S to V, and we gave an argument. all of these proofs are by induction. Like everything is by induction over something, typically over the number of visited vertices, which is kind of like saying that you're doing an induction over various phases in the algorithm. So what this means is, so if you look at the sort of the BFS code here, this is an induction over how many times a particular loop runs. Either this loop or it's saying how many times does this part run, which is equivalent to saying that you're looking at BFS at a particular stage of the algorithm, an intermediate stage. You're saying, suppose some part of it is true. After one more iteration, does it still hold? And if that holds, then that's what induction is doing. And the reason why induction is so fundamental to all computer science algorithms proofs is because pretty much any useful algorithm that we have has a loop. Right? And arguing that a procedure that loops is correct or arguing something about it is basically induction. Does that make sense? It is not, I mean, maybe this is clear to most of you, but I'll repeat this nonetheless. The typical examples of induction that you'll see are like these, there's like some math formula you need to prove, right? Like the sum of the first n natural numbers, the sum of the first n squares. And so you have this formula and then you do this sort of plug and play to try to prove that f of n plus 1 is true, assuming f of n. Right? So someone once asked me, what is f of n here? And so it's a bit complicated. F of n is actually the statement of the loop invariant. That entire statement is the induction hypothesis. That makes sense? So for example, in this case, what is the induction hypothesis? The induction hypothesis is this statement up to k visited vertices. Which is like saying that you're assuming that this statement is true up to some point in the algorithm. And then you're arguing, the induction step is to argue that it is still true after the next step. Yes?
So, let's say we are talking about sum of n positive numbers.
Yep.
And in that we say this is the, it's supposed to be the formula.
Yep.
And then we prove it by induction.
Correct.
But we come up with the algorithm just by intuition first and then prove it? Or what's the first thing to get the algorithm?
So the algorithm usually, so the way this works is different, right? Usually you come up with the algorithm before doing all this induction stuff. You want to then prove that the algorithm is correct using induction. For doing that, you have to discover some kind of loop invariant. So this is the hard part usually. But, so once you discover the loop invariant, which is not particularly easy, you then have to prove that this loop invariant is correct, and that's where you're doing the induction. Does that make sense? So it takes some getting used to do these. And my hope is, you'll see, what's happening in class. You'll do this homework where you're actually going to prove this using induction, where I've kind of broken it down step by step. Okay, this is not what I was going to talk about, but given that question, I might as well talk about it. So you look at the statement, right, and you say, how on earth are you going to prove this? Like, how do you mathematically argue that this is correct? So the way that the induction works is, you see this, it says at the beginning of the while loop, something holds. So suppose the statement held at the beginning of the while loop after k iterations of the while loop. You now need to argue that it's going to be true after one more iteration. That whole process is the induction. So it's like saying if something is true after k iterations and it's true for the next iteration, you keep doing induction, you know it's going to be true, and the base case is true. Which usually it's very easy to argue the base case here. In the base case, what does the Q look like? It just has S. Right? And when it just has S, you can see that all of these things are all sort of trivially true. The Q is sorted by distance, of course. There's only one thing in the Q. All the vertices of distance d or d plus 1, that's trivially true. All the vertices that have been dq'd, no vertex has been dq'd. And everything that has been visited has distance at least 1. Yes?
So the loop invariant proves the base case.
No. The loop invariant has a base case. The base case of the loop invariant is the very beginning of the algorithm is the base case. Does that make sense? So it's like when the queue has only one element, which is S, that is the base case. Does that clarify that? Yeah, more questions. You should ask questions right now because the homework will depend on this, and so understanding this is useful. Yes?
So in this case specifically for the third statement,
Yeah.
your base case doesn't talk about anything being DQ'd yet. So do you start with your base case with like what?
So this is okay, so good. So in that case, the base okay, just to be clear, you don't do you don't do induction first on 1, then on 2, then on 3, then on 4. Assume that all of 1, 2, 3, and 4 are correct up to some point. Then you prove all of 1, 2, 3, 4. Does that make sense? So the statement 3 in the base case is called vacuous, meaning that it's a sort of trivially true statement because nothing has been DQ'd. So like statement 3 isn't really saying anything in the base case. But in the other cases, of course, it's saying something. Yeah?
Still a little bit confused about like what proved by induction is. If I understand it correctly, is it like you prove that every iteration up to n is true, so therefore n plus 1?
Yeah, so let's not use the letter n because n is usually the number of vertices. Let's use k. So what it's saying is that suppose the statement is true up to k iterations, it's going to be true for the next iteration. Okay, what the heck? Let's do it. Forget it. Right? I mean, okay. Not this. We're not going to do this because this is part of the homework. But I'm going to do the proof of the BFS theorem, and let's just walk over some induction arguments. Okay, so I guess we're not going to finish BFS soon, but it doesn't matter. Okay. That's why you should ask questions, because if you ask more questions, then you can derail me and then you'll actually understand something. Otherwise, I'll just keep going on. Okay, good. So should I read over this argument again? Yes, no? Okay, all right, I will. Few people nodded. So what are we doing here? Again, we're proving the BFS theorem, assuming the loop invariant. Clear what that means? Right, we're assuming that this statement is true at all times. Now we're going to show that these statements are true. So first let's show this part. This has two parts. First part, if visited V is true, then there is a path to S. This is what we need to prove. So we're going to prove this statement by induction on the number of currently visited vertices at the beginning of the while loop. Just reading what I've written, right? So this is like the number of iterations, which is kind of like, it's the same thing as the number of iterations of the while loop, but you can also think of it as the number of visited vertices. Okay? So what is the base case? This is like 0 iterations of the loop, which means that only S has been visited. Right? Because if you recall the algorithm, before anything is run, S is visited. Okay, so only S is visited. S is obviously connected to S, so the statement is true. Now, what is the induction? It says, assume true up to k visited vertices. So when the next vertex V is visited, V is a neighbor of U, which was DQ'd. Right? Because you remove something from the queue and then you visit V. Now, let's look at the loop invariant. It says that all vertices that have been DQ'd have a distance of at most D. So obviously anything that's been DQ'd is connected because it has some distance. And so U has some distance to S, U is connected to S, and if a vertex V is connected to something, is a neighbor of something connected, then it is also connected, and so this completes the induction. Right? So you go from one step to the next. Does that sort of clarify how an induction goes? Yeah? Yes?
There's a couple of different versions of induction, right? You can do it with k plus 1, k minus 1, and I think there's like 1 half.
Sure, yeah. It doesn't matter which one. Often, what we're doing here is maybe strong induction. We're assuming it's true for everything up to k and not just k to k plus 1. That's typically what we're doing. Yeah. Anything else? Okay, so let's go ahead and do the next one, right? So the next thing we need to argue is if there is a path from S to V, then visited V is true. Does this make sense? It's actually the harder part of BFS. This is saying that if anything is actually connected, BFS is eventually going to visit that. And so this, again, to prove it formally, you have to structure it as some kind of induction. And the question usually is induction over what? Now, if you think, oh, I'm going to do induction over the number of times the loop goes, that's a bit tricky because somehow how do you relate that to this specific V? So intuitively, what's going on? There's a path from S to V. Why do you think V has to get visited? Why should V eventually be visited? Yeah? Sure, yes. There you go. There's a loop invariant. Yeah. But for a moment, ignore the story of the loop invariant. Just tell me, like, intuitively, like, what is your reasoning for that, yeah? Okay, every neighbor of V should be visited. Why? You're getting towards the induction, yeah?
If there's a path from S to V, there should be like V should have some distance from S.
Okay.
So each step will be maybe increasing the distance by 1, right? And we should eventually hit V and visit V.
Okay, good. So if there's a path from S to V, then V has some distance to S. And so it seems that at some point BFS should visit everything of the previous distance. Yeah? All the neighbors. So you're basically getting closer and closer to the statement. You're saying that, look, if there's a path from S to V, then V must have some neighbor that's even closer to S, and that must have some neighbor that's even closer to S, so on and so forth, all the way up to S. And so somehow once S is visited, then the next one should be visited eventually, and then the next one should be visited eventually, so on and so forth. Right, so you sort of have to combine these insights. So one is basically, if there is a path from S to V, you expect that some neighbor is going to be visited at some point. Who is that neighbor? It's the one that's closer to S, I'm sorry. And then it seems that it would be useful to understand distance. So essentially, suppose we did induction over the distance. Okay, I'll say this and then I'll go ahead and write it. So if there's a path from S to V, then V has some distance. Let's do induction over that distance to prove the statement. What is the base case? Distance is 0, visited S is true. Sure. Then we say, suppose everything up to distance D has this property. Right? Now, because visited V is true, that means that all vertices up to that distance have entered the queue. And if they've entered the queue, they've also left the queue. And if they have left the queue, then all their neighbors will enter the queue. And then that's why this vertex at distance D plus 1 would have entered the queue. And if it enters the queue, it will get visited. So that's sort of the chain of reasoning. I'll write this down. Okay? And once I write, hopefully this will be clear. Okay. Okay? So I'll say that we prove by induction over the distance dV of V to S. So maybe I'll just, okay, I'm just going to call this D prime. The reason I'm not calling it D is because we've used D so many times in the previous proof that I want to distinguish this as a variable. I don't want to overload that variable. Okay, so we'll prove this over induction over the distance D prime of V to S. So the base case is D prime is equal to 0. So we have to prove this statement for everything whose distance is 0. There is only one vertex whose distance is 0, which is S, and we know that visited S is true, right? The only vertex V with distance 0 is S, and visited S is true. Okay, so we know that. Yes? Because we initialize, yeah, that's true. So our visited V is true by the initialization. Okay? Because of the initialization. Okay. So that's the base case. So now let's do the induction. Okay, so induction, we will assume true up to all vertices V of distance at most D prime. So just for the comment, I'm doing strong induction here at most D prime, although you can do it with weak induction, it doesn't matter. It just makes it easier. So what does this mean? It's saying that what we're assuming is that BFS is going to visit all vertices whose distance is at most D prime. This is just saying that we assume that BFS visits all vertices V of distance at most D prime. Now we need to argue. We need to prove BFS visits all vertices at distance D prime plus 1. Clear? Right? So we need to prove that BFS visits all vertices at distance D prime plus 1. Okay? So consider a vertex V at distance D prime plus 1, right? V must have a neighbor at distance D prime. So I'll call this neighbor U. Right? If it's a distance D prime plus 1, there's some neighbor that's closer. Right? That's just by the fact that there is a path of a particular length. Right? And so now you can apply the induction hypothesis on V. Yes?
That doesn't mean that the neighbor is the father, the parent?
It does not mean it's necessarily a good question. We don't know if it's a parent or not. It doesn't have to be. It's a good question. I'm not saying that it's the predecessor. I'm just saying there's some neighbor. But just because it has distance D prime, which is 1 less, I can apply the induction hypothesis on it. Okay. Some people get confused with induction proofs because they look like a bait and switch. They look like you're just using the same thing to argue. It looks like it is not circular because I'm starting at distance D prime plus 1 and going to distance D prime. And if you really uncoil the entire induction, then from D prime you would have gone to D prime minus 1. And then from there to D prime minus 2, all the way down to 0, which is the base case. So if you kind of chain it together, it makes sense. S was visited, so all neighbors of S are going to get visited, which means all neighbors of it are going to get visited, and so on and so forth. You're just reversing this process. How many of you have written code in a functional programming language? You have, right? So hopefully this is kind of like a functional programming language, right? That's the way you think. You don't think bottom up, you think top down, right? Because you think recursion. And it's the same thing. It's the same thing. So for those of you who haven't written code in a functional programming language, it's usually quite helpful. I think it actually helps understand recursion, which is the same thing as induction. right? They're basically the same thing. Right? The problem with loops is when you think about loops, you think bottom up. Right? You think, oh, this loop, oh, I'll just keep doing this, and then that's how you write the loop. And when you do functional programming, you think the opposite way. And I think that opposite way is usually the harder one to understand, but is the more mathematically precise one. Okay? All right. So V must have a neighbor at distance d prime by the induction hypothesis. And what is the induction hypothesis? That's that. U must be visited. Now, what does it mean for U to be visited? Every visited vertex enters the queue, right? So, U entered the queue. And so if it entered the queue, it must have also exited the queue. So U got DQ'd. Right? And what happens when U gets DQ'd? All of its unvisited neighbors get visited. Right? So all the neighbors of U have to be visited. Because if they're not visited, then they would have entered the queue and gone visited, right? So that's basically this step. Okay, U got DQ'd, and so all neighbors of U get visited. Like either they were visited before or they get visited at that step, but they all get visited. Yeah. So V gets visited. That's the induction. All neighbors of U get visited, so V gets visited, completing the induction. Yeah. Question here, there, and there. Yeah.
Why do we use d prime instead of just d?
I'm just using a different variable so that I want to distinguish this from the d that I wrote in the back. I mean, it's just thinking of it like when I write two pieces of code, sometimes I just use a different variable name here just to tell you that they're different, just not to overload the notation. Make sense? Yeah. Behind.
Again, the same question. That what you just said is meaning that the predecessor is you. The predecessor of V is you.
No, so the thing is there could be multiple neighbors. So it could be that maybe V had two neighbors, U and W, both at distance d, and I'm not sure which one became the predecessor. It could be the fact that when U gets DQ'd, V is already visited because of some other neighbor. I'm not claiming that this is happening because of U. I'm just saying that when U ends, all the neighbors end up being visited either from before or at that step.
But at that point, when it ends, it is the predecessor.
No, so let me give you an example. So I'll draw this here. So let's just say that this is S, this is V. I don't necessarily know which of these is going to become the predecessor when I look at the graph. It all depends on how everything is ordered. So, and then this proof doesn't necessarily, it just says that V has a neighbor at distance d prime. That neighbor could be U or it could be W. I don't know which one. So it could be the case that maybe V prime was the first one that got visited. That would already insert this into the queue. So when I DQ this, V prime is already visited. The predecessor of this was actually W, or V was W. So right? So I don't know. Yeah. Sorry, someone, you had your hand up, I think.
You answered my question.
Okay, there's a hand up with my hand.
Am I correct in understanding that the concept of a predecessor is only relevant in the shortest path that is determined? Kind of without that, it's just neighbors.
Yes. How did I come up with this one? Well, okay, so that is a good question. So the thing is, based on like the discussion and thinking about it, it seems like an induction over the distance is the right thing to do. And once I kind of guessed that, okay, that is the right thing to do, I did it. The answer is I've been doing this for a decade, so I can do this like in and out. And that's the unfortunate answer. Like it's difficult. Like, you know, how did I come up with this? Because it seems like once I came up with it, then the proof was not that hard. That's just like saying that, how do you come up with this? Once you come up with this loop invariant, then things line up. Practice.
Sorry, can we go back to the diagram?
This one?
Yeah.
That one, yeah.
So just to like clarify, like when we say like all neighbors of U get visited, like if you had two other neighbors like X and Y, then we would be saying that definitely like if V is visited, X and Y must have also been visited.
Well, yeah, but then I would reason it differently. So it could be that X and Y could have actually been closer to S.
Okay.
So maybe they got visited even before.
Okay.
But the whole point is that when a vertex exits the queue, all of its neighbors are visited, either because of you or maybe they just got visited before. I don't exactly care in this proof how that happened, because I'm not talking about the predecessors. Yeah?
We assume BFS with the all vertices would be of distance
D prime.
D prime. But like U and W is also in the distance of D, but so they have to be visited.
That's right. U and W have to be visited.
And that example is not. You just said that the example is that U is visited after V is visited.
No, I didn't say U is. I said U is DQ'd after V is visited. U is DQ'd after V is visited. That's what I'm saying. Like the question that he asked was like, you know, am I not just saying that the predecessor of V is U? And I said no, because maybe V was visited before U exited the queue.
And at the same time, U is also visited.
U was already visited, yes. The reason for the predecessor is the predecessor of V becomes U only if V gets visited when U exits the queue. Like if V got visited because of U, then U is the predecessor. I am not saying here that V is visited because of U. Like I'm not sure. But all I know is that when U exits the queue, all of its neighbors get visited. All of its neighbors are visited, either because of U or from before. Right? So this statement over here, all neighbors of V, maybe I should say are visited. And I'll just clarify this. Either because of U or from before.
Sorry,
Yeah.
I think it actually might make. You said it earlier. Have been, I think, makes the most sense instead of are. Just like semantically. Like,
Yeah. Okay. Fine. Yeah. Sure. Yeah. All of when yeah. Yeah. Have been. Sure. But yeah, does that make sense? I mean, again, like it's, you know, these do take some getting used to, and I promise you the right way to do it is instead of hearing me go on and on about it, you have to do a few of your own, and then it starts making more sense. Yeah.
And then I would just change like so V has been visited.
V gets visited. Okay. Sure. Okay. I will. I would just say V is visited. So, But anyway, it like, I'm not going to pick if false with your, choices of the verb here. But what I do want when you write this is that, it's a sort of logical, you don't do what are called non sequiturs. So what is non sequitur? It means it does not follow, which means that you just suddenly say something, jumping a step. Right? So what you want is to make sure that you get a logical sequence. So maybe I'll do another one just to make this even more, clear. Okay, so this is statement 1. I'm not going to prove statement 2. I'm going to tell you statement 2, it's easy. You don't need induction, no induction. Just use 1. Okay? Just use the first statement, think about it a bit, and you'll do it, I'm pretty sure, yeah? So in the homework, you're going to prove the loop invariant, so none of this enters the picture. So it's like you're doing you're actually doing the core part of it, which is actually what we've assumed over here, right? So, yeah. Okay, so 2 is easy. So let's do 3, which is maybe... Okay, so let's prove this one. For V connected to S, the path is the shortest path, right? Which is sort of the heart of the matter. So again, it seems like you have to do some induction. And by now, when you're thinking about BFS, the typical things that you do, there are like 2 things that you induction on. Either the number of times the loop runs, or like the number of visited vertices, or you do induction on the distance. Right? And so usually one of these is what you need. Yeah? Sorry. Which I don't even know what you're talking about, unfortunately. So I've forgotten. Okay, so I'm going to take a break for a couple of minutes because I think I've spoken too much. Right? Okay? So I'll give you a few minutes. And then when we come back, I'll write down how to do this. But you can also think about it in those 2 minutes. I need to oh, that camera. Oh, I see. Yeah. Okay, so let's continue. So I want to prove this third part, which is that for V connected to S, the path V, predecessor of V, predecessor, predecessor of V, so on and so forth, is the shortest path. So let me just do some setup, and I'll say for V connected to S, visited V is true, and this is by part 1. So V must enter the queue at some point. Right? So this is and what we'll show is that as soon as V enters the queue, that's when the predecessor gets set, and then we can do some sort of induction to get that to work. Okay, that's sort of the overall idea. So what I'll do is I'll do induction over the number of entries to the queue, right? Because that seems to be the relevant point here. Again, how did I discover that? Well, again, I've been doing this for years, but you'll do a few of them and you'll kind of get the sense. So typically for every algorithm like BFS, after a while you start seeing the pattern. That is typically induction on something with the queue or the distance, because those are sort of the only relevant aspects of the procedure. Okay, so we'll do induction on the number of vertices that enter the queue. And so again, the base case, so the queue is just, is just the set S, right? It just has one element S in it, and so obviously S to S is a shortest path. This is sort of vacuously true then. So there's nothing to do in the base case. So now let's do the induction. So assume true up to k vertices that have entered the queue. So essentially for every vertex that has entered the queue, we assume this is true, right? That if you follow the predecessors, you end up with the shortest path. Now consider the next vertex, V, that enters the queue. Okay, so now what we do is we look at BFS again, and we say, why did V enter the queue? Well, it entered because it was the neighbor of something that was just removed from the queue, and it became the predecessor. Like, U became the predecessor at that point. Okay, so I'm just going to write this down. So consider the next vertex that enters the queue. V entered the queue at this point, or maybe at this time, because, so I'm going to write down a few things. V is a neighbor of U. V was unvisited, and 3, U got DQ'd. Right? That's basically what happened, right? And I'll say, again, this is, if you really want to be precise, I'll say this is all happening at step 3, 2. Right? Like right at this point, why is V going to enter the queue? Well, at this point, V is not visited. V is a neighbor of U, and U got DQ'd. Like we're saying, at that point, this is what happened. So does this make sense at this point? Okay. And so we will set, or rather, BFS will set the predecessor of V equals U. Right? Now, why is this a shortest path? Right? That's the trick. Yeah? No. So I'm going to say that, okay, I'm going to write a few things and then I'm going to show you the loop invariant, then hopefully it will be clear. Okay? So BFS will set the predecessor of V to be U, right? Suppose, okay, so the distance of U is D. Yeah? Hang on, sorry, let me just write something and then you can say what you need to say. Okay. And then by the induction hypothesis, before, what do I know by the induction hypothesis at this point? I know something about U. Because U has obviously entered the queue. Because U is getting DQ'd. So by the induction hypothesis, I know that this statement is true for U. Right? So if I start from U and take predecessors all the way, I know that's the shortest path. So let me write this down. So by the induction hypothesis, because U has already entered the queue, U predecessor of U, predecessor of U, all the way back to S is the shortest path. And because I assume the distance was D, I'm saying this is the shortest path, and this has length D. Clear? Yes? No? Okay, now, why is it the case that if I start from V, this is the shortest path? I'm going to put up this loop invariant, and then you had something to say.
Yeah, I think
Why?
I was thinking about is that all the distance up to U, if you assume that is D,
Yeah.
then the next neighbor or the next level would have distance D plus 1.
Right.
And so if we actually, our hypothesis essentially is for U, D, then because of the fourth point, we can argue that.
What is the fourth point? Okay, yeah. You mean the loop invariant? Okay, good. So you're using the loop invariant, and you're saying all the vertices that are not visited have distance at least D plus 1. You have, yes.
Can we also use 2?
All the vertices in the queue, but then V is not in the queue. You're looking at the point at 3, 2, where V is unvisited, has not entered the queue yet, right? But you probably could also do that as well. You look at a different point in the algorithm and you say, oh, V is now in the queue, so it has distance D or D plus 1. But how do you know it doesn't have distance D already? See, what you need to show, okay, so maybe let me ask this question. Maybe I'll ask this. Get the post-its out. What is the distance of V? Is it D? Is it D plus 1? Or is it strictly less than D? Okay. So give you a few minutes to ponder that. So at this stage, what do you think the distance of D is? Yeah, what is the answer? That's right. It is D plus 1. So you intuitively know that, but you have to prove that the distance actually is D plus 1. And so how do you prove that it's just D plus 1? Which is, yeah? Loop invariant. Yep. Yeah. So by the way, unfortunately, there is a 1 and 3 here, and there's a 1 and 3 here as well. So it's confusing.
1 and 3 both
Of the loop invariant. But why does the queue being sorted by distance really, why is that relevant?
meaning that the DQ vertice has the smallest distance.
Okay.
The third one's the same. I think it could probably work just using the third one.
Possibly. Yeah. Just use 4. Yeah.
If U is DQ'd and V is a neighbor of U, that means
You don't know. The things in the queue could have D or D plus 1.
But if the parent node was DQ'd already, doesn't that mean? Or,
It's just 4, right? Because if you look at 4, it says V was unvisited. Right? V was unvisited and the distance of U is D. So at that point, all the vertices that are not visited have distance at least D plus 1. So V must have a distance of at least D plus 1. And because V is a neighbor of U, its distance is at most D plus 1. So if it's at most D plus 1, at least it is D plus 1.
This could be a silly question. So, what if there's two paths from V to U, one where the step is D plus 1 and one where the step is D plus 2? Since there's no upper bound on the fourth clause of the loop invariant, is there like a forward bound?
Good question, right? So you're good. So you're saying 4 doesn't give any upper, it only says it's at least D plus 1. But because V is a neighbor of U, I know that there is a path that is at most D plus 1. There's actually a path of D plus 1. So if there's a path of D plus 1, and I know the distance is at least D plus 1, then it has to be D plus 1. Answer your question? It's like a very tightly fit together jigsaw puzzle, right? Like everything, like, by the way, it's very hard to sort of get all of this just by sitting through one lecture, right? So you kind of have to go back and read through it, and you'll actually, and if you really spend some time with it, you'll see how the pieces fit really tightly. Yeah.
It's not that I don't get it. I get it. But what my problem is with the writing when we give you an answer. We don't have to prove that there's not any other path that have distance, I don't know, less than D plus 1.
You have to argue, it's like you're arguing that what you're saying is that, look, when V is discovered, like right at that point at 3, 2, right here, you're trying to argue that V could not have been any closer. How do you know that? You know it only because of the loop invariant.
Yeah, but where do we say that? Where do we prove that?
This loop invariant?
No. The thing that when you found V, that's like the shortest path.
So I'm going to write that down right now. But the argument for that is through the loop invariant.
Okay, and a second question that we got here is, like, we know from the bottom part of where it says BFS will set predecessor B equal to U. Because of that, we don't know already that the distance is D plus 1.
You don't know the distance is D plus 1. All you know is there is a path of D plus 1. You have to prove that it is the shortest path.
But we are saying that the predecessor of B has a distance of D. So the next one will be D plus 1.
So what you're implicitly assuming is that the predecessor is giving you the shortest path. Like you've already internalized that fact. You have to imagine that that is not true and argue that it is true. Right? So the problem is that you've heard about BFS so many times and you've thought about predecessor so many times that in your mind, predecessor means it is going to be the shortest path. But I'm telling you, how do you know that is true? This is the process to prove that that is true.
So going back to that person's point earlier about like, can you go to the loop? Oh yeah, I can hear. So like basically, the distance of V we know is D plus 1 because number 4, which we already talked about, and then also number 2. And can we argue that based on number 4 and number 2, all vertices in the queue that have not been visited must have a distance of D plus 1?
You could also, I mean, by the way, if it's in the queue, it's visited.
Oh wait, okay, maybe I got confused.
But you can do it multiple ways. But I think sort of the most transparent way is to basically just say that by 4, at this point, the distance is at least D plus 1. And look, we actually found a path of distance of length D plus 1, so the distance is D plus 1. Yeah.
Can you argue that a vertex as it is entering the queue always has a distance of D plus 1?
Yes. That is exactly what we're arguing here. Yeah. No, it's a hypothesis. So you don't need to. So the process of induction says that if you can use it as a hypothesis, then overall it's true by the process of induction. Yeah? Needs some getting used to. Yeah. So so think of it like a chain, right? You're basically saying that if the chain is correct up to this, then I know the next one is true. And I know the first one is true. Therefore, everything is true.
What about something at the beginning of the proof? We say that true up to K or over.
Yeah.
Then we assume, right?
This is the induction hypothesis.
Okay, so it's the same thing.
This is the induction hypothesis. Yeah. So this is a funny quote, but so do you know who von Neumann is? John von Neumann? Like one of the most prominent mathematicians of the previous century. I mean, essentially pretty much anything that you lay your hands on in computer science or math, if you go back a little bit, it's von Neumann. Like von Neumann defined basically the computer architecture, that we all use. Von Neumann did most of the math for everything. So von Neumann, once he was teaching, and then some student says, something in math, and the student says, but Professor von Neumann, I don't understand what's going on. And he says, young man, in mathematics, you don't understand things, you just get used to them. So this is exactly like induction, right? At some point, you just get used to it. Okay, so let's sort of complete this argument. So I'll say, by part 4 of the loop invariant. Oh, sorry. By part 4 of the loop invariant, since V was unvisited at the step 3-2, V has a distance of at least d plus 1. V is a neighbor of U at distance d. So, the distance of V is at most d plus 1, right? Because it has a neighbor of distance d. So, the distance of U is d plus 1. And now we'll say the path V, the predecessor of V, which is equal to U, and the predecessor of U, the predecessor of U, all the way back to S, has length what? Is d plus 1. Why is it d plus 1? Because you know that from here to here, by the induction hypothesis, it was d. There's an extra plus 1. This has path d plus 1. So this must be your shortest path. Right? Because the distance is d plus 1, and you have a path of length d plus 1. So, okay, I've run out of space on this piece of paper. Sort of complete that here. Hence, this path is a shortest path from V to S, and this completes the induction. By the way, for the first homework especially, the first math homework, because you're still getting used to induction proofs, usually what I do is, if the TAs find an error, they'll mark the error, they'll show it to you, and then you can correct it and go back. Right? Because, but don't abuse it. Like, don't just go and say, oh, can you give me one more point? Can you give me one more point? When they give you an error, and if you understand it, you can fix it, yeah?
We don't have to
Uh-huh.
We don't have to argue that since V hasn't been queued, then there is no other shortest path.
You don't really need to argue. Because there can be multiple shortest paths. All you need to argue is that whatever is found is one of the possible shortest paths. Someone had their hand up here. I forget. Maybe, yeah.
How are you proving? Is it because predecessor of V is equal to U and prove that V is equals 1?
V is a, sorry, yes. Uh-huh.
Is that how we know it's the shortest path?
So we know it's the shortest path because you know that the distance is d plus 1. And you know the distance is d plus 1 because of a combination of two parts. By part 4 of the loop invariant, it was unvisited, so its distance was more than d plus 1. It's a neighbor of something of distance d, so its distance at most d plus 1. So those two together means the distance has to be d plus 1. So any path of distance of length d plus 1 is a shortest path. And this happens to be one such path. Yeah.
So, we have been having this conversation on why it's the shortest path, but the entire proof that we have depends on the loop invariant, which we haven't proved.
Exactly.
We won't be making similar arguments for like a different algorithm, let's say BFS,
Uh-huh.
because its loop invariant might be completely different.
Exactly. Its loop invariant is going to be completely different, which when we get to DFS, you will see. But the style of argument you'll see is sort of similar. The style of argument is, again, there is some loop invariant. There's some notion of progress of the algorithm, right, where progress is being measured either with the queue or with distance or with something. And you do induction over that notion of progress. Okay? Okay, so I'm going to stop. Okay, so at this point, we've done all this stuff about loop invariance and BFS. I'm going to say a few more things about BFS, and then good riddance. Like, we can move on to other things. I will move on. You won't, because you have these homeworks to do on BFS. But just sort of as a pedagogical comment, I've always struggled, like, is there any utility to me teaching these proofs? Because, I mean, there are a few of you who might have to do this for a living, but that's a relatively small number of people. If you end up in theoretical computer science or the analysis of algorithms, then this is your day-to-day job, like it is for me. But I know that is not the case for most of you, so why am I teaching this? And you can contradict me on this. But the way that I look at it is that this is something that you normally don't see otherwise. Like, how do you formally analyze an algorithm? And I feel that this thought process is like really good mental exercise. So that when you go on to try to basically explain or understand some complex process, you have some mental model of breaking things down. You don't necessarily go around in industry saying, oh, let me show you something by induction. But you sort of have this thing that, okay, let's say that something is true up to some point. Let's see what happens at the next step. To be able to break things down in that way is very useful. Right? And that's why I think BFS is a useful pedagogical tool towards that. But the only test is some of you have to come back to me 3 years later and say, yes, it was useful. Okay. But regardless of that, I think coding up BFS is useful. So that's something that you will get. Okay. So far, so good. So what we did is we did this notion of BFS from a starting vertex, and we did all this stuff on it. There was a comment that I had in the assignment, and I also mentioned, what does it mean to do BFS on the graph? So it's a really simple thing. What you do is you simply initialize all predecessor to null and visited to false. And then what you do is, for each S in the vertex set, you simply say if visited S is false, then you run BFS of S, and I'll say do not create new copies of predecessor or visited in BFS of S. So it's kind of like you set this global variable predecessor and visited, and you just run it in this way. Does this make sense? So, yes?
So this is basically just to make sure that every single part of the graph, even if it's disconnected sections, all get visited.
Exactly. This is so that you, so this is what, so there's, I mean, this is sort of a semantic, like BFS of S is often called like, single source BFS, or like BFS from a source, and BFS on G is like running BFS on the whole graph. Note that you're not running BFS from all possible sources. You're not doing that. Why is that? So I'm just going to draw a picture over here. So let's just say your graph looks something like this, where these are all what are called the connected components. Now, you don't know how S is ordered or anything about it, but eventually you're going to pick some S in here, and that's just going to visit everything. So when this loop proceeds, it's never going to touch any one of these again. And then it's going to find some vertex here, and then it's going to visit everything here. And then it goes here, it's going to visit everything here, visit everything here. So you don't get all shortest path information, because you're not running all possible BFSs. Yes?
If you were to do that, it would multiply the time complexity by n.
By n, exactly. And that would be mn, quadratic. This runs in this just runs in linear time. Right? So the output is what is called a BFS forest. Right? Because for each of these, you're going to get some tree of predecessors here. And then for this, you get a tree of predecessors here. And so on and so forth. Right? So the number of trees that you get is the number of connected components. And I'll leave it to you to figure out how to count the number of trees, because you're going to have to do this for the homework. Okay? So each tree, does forest make sense? It's a collection of trees. Yeah?
So basically the output is basically like what you drew there. It's like it's separate like forests.
Or separate trees.
Okay. Gotcha.
So imagine that like you're running BFS of S for one source in each of these components.
Okay.
Yeah?
So is each tree in the forest a shortest path?
It is a shortest path tree from that source. But you don't know which source you pick, because you're just looping over everything.
So do you just start, so you have your list of nodes, right? And you start at the highest one that's not visited. And then you complete your tree, and then you start the next one that's not visited.
Exactly. So the thing is that, but think of it as, and especially in the example that I gave you, in the homework. So I don't know if anyone has opened the files and looked at it, but it's a credits thing, right? So it says movie, actor, 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 movie, actor, actor. So what you need to do is you have to parse through that file, create a graph of actors, but you don't know what the connected components look like. You don't know anything, right? But you can get the list of all actors from that parsing. So you have a list of all actors that are there. How do you find connected components? You'll just put this list down as a Python list. You'll start from the first thing. I say, go ahead and run BFS. It's going to end up visiting a bunch of them. It might visit the next one, it might not, you don't know. But then as you loop, you'll basically get all the connected components.
Well, it's not related to the homework, but so is it possible in forest for like the same source node or the same end node to have different source nodes?
No, so that's good point. So the thing is, because the way I set it up, note that when I do visited S is false, right? So all of these are going to have visited S equals true. So I'll never visit anything again. So it's important that you don't create a separate copy of the data structure every time you run BFS. Do not write this code by just calling that previous code, because that previous code has a local copy of each visited. You have to have one global copy. Okay? And these are the implementation things you'll see when you write the code for it. So the code for BFS S and BFS G is actually not that different. It's just that whether you're using predecessor and visited as a global or a local variable in each. So each tree is a connected component, and the running time is O of n plus n, not m times n. It's not like you're running n BFSs. Actually, how many BFSs do you actually run in the end? It's the number of connected components. So if you only have one connected component, you'll just run one, and that's it. Yeah?
Can I ask you a question about some specifications in the homework?
Sure.
I know we have to take into account the case where there are different movies with the same name,
Yes.
but do we have to take into account different actors with the same name?
No.
Okay.
I mean, maybe there are different actors with the same name that might. Actually, I think that officially, according to the Actors Guild, they have to choose a different name. So it's unlike. That's why they will often change their names. So I think that they're all different.
What if they just said that to be spicy? Like, I didn't.
I think there's actually a rule. By the way, the data is it's a little outdated, right? So I scraped it a few years ago, but whatever. So don't expect to find the latest and greatest movies, but you'll see interesting stuff there. Yeah.
Sorry, one more question.
Yeah.
Is it recommended or acceptable to change like your graph tool?
Sure. Yeah, you can do whatever you want with it. You don't even have to use it.
Okay.
But it just might make your life easy. Yeah. Yeah.
Even if I account for movie names being different, do I have to like notate which of n movies have the same name?
No. You don't. I mean, I'm just saying that be careful when you construct the graph because there are multiple movies with the same name. So let's say you have two actors who acted in, I don't know, some movie, I don't know, The Terminator, say. And let's say that there are two versions of The Terminator. Then there would be another one which has The Terminator, which has two different actors. You don't want to connect up the actors that have acted in different movies that have the same name. You have to be careful because that will then create an error. You'll get wrong paths. So just be careful in the parsing. Yeah.
Small tangent now is that like it could be the same movie. Would it be the same movie but just like actor A and B have done it and actor C and D?
No, they're two different movies that have the same name. So each line is a different movie, but they could be the same. The name might be the same.
Okay, so those actors are connected, but the movie name is.
No, I'll say this again, right? So maybe I'll write it on the board, right? So I don't know. Let's just say that there's one line that says foo actor 1, actor 2. And then there is another foo actor 3, actor 4. So this means that there happens to be one movie called, I don't know, Godzilla. There is another movie called Godzilla. But that doesn't mean that actor 1 and actor 3 acted together in the same movie. It's just actor 1 and 2 who acted in a movie and 3 and 4 who acted together. Right? That's the point. So I didn't go and actually like disambiguate these. Like technically if I use the year or something, then usually they're different. Okay, so why do you need BFS of G for that assignment? Because I've asked you to count the number of connected components. I've given you two graphs. One is basically a subsampling of the other one. So you'll see that one has, the subsampling has more connected components. Okay. Last couple of things on BFS. So I'll just say that like the thing about things like BFS and DFS is they're not just an algorithm to do one thing. They're usually used to do lots of different things. So just as we talked about, we did shortest paths. You can do connected components. I'll tell you another classic application. So a graph is called bipartite if it looks like this. That is that all vertices can be partitioned into two parts and all the edges only go across. So V can be partitioned into L union R such that all edges go from L to R. So like, let's say you have, yeah?
Does it mean there are no internal edges from L to L?
Yes. It means that no internal edges from L to L, no internal edges from R to R. But suppose if I just gave you an adjacency list, just like I've given some adjacency list, how do you know the graph is bipartite? How do you determine if a graph is bipartite? And actually you can do it using BFS. So this is also called two-colorable, which means that color the vertices so that no edge goes between vertices of the same color. And so BFS can be used to determine if a graph is bipartite. And so you can do this in basically O of m plus n time, which is linear time, like it's just once in the size of the input. Yeah? So I'll show you a generalization of this, which is, so often people will construct specific kinds, like for example in actors, so one is the co-actor graph, another one people will do is called the actor-movie graph. So movies on one side and actors on the other, and you have edges that go if an actor acts in a movie. Now let's just say you share this data set with someone. One of the things people will check is like, is the data corrupted? And so you just check is the graph bipartite, because if not, then there was probably some corruption in the data. So there are certain kinds of representations that are all bipartite. A lot of like what happens in Netflix in their movie recommendation system is they construct a graph which is like users and the movies they watch. So they'll construct this bipartite graph. And then they're actually trying to predict what you would what you would click on. So the data that they already have is a bipartite graph, and they're trying to predict what new edges will form. And that's how they actually determine how to recommend something. So the representation of a lot of data is bipartite. And so you will often you might have an algorithm just to check it to make sure that you don't have any errors in your system. So this is bipartite. What about tripartite? So a graph is tripartite if it looks like this. And this is also called three-colorable. Right? So you could say, oh, there's an algorithm to determine if a graph is bipartite. That runs in linear time. Is there an algorithm to determine if something is tripartite? Like an efficient way. Like maybe you do some version of BFS or DFS or something. And it turns out that this is actually related to something called the P versus NP problem. Like we do not think there is an efficient. By efficient, I mean that something that runs in polynomial in NM time algorithm for this problem. So it's kind of crazy that for this problem, there's something that you can learn basically like, your first graduate algorithms course, you see an algorithm to do it. But whether you could break it into 3 parts, we don't have any efficient algorithm. Which is, yeah?
Well, I think I've seen this before, but what does P and NP stand for?
Okay, that would be another lecture or a few. But think of it one way is that P is like efficient algorithms, and NP is it's called efficiently verifiable. Let's leave that aside. You ask me later, ask me during office hours. But the point is, just when you go from breaking it into 2 parts to 3 parts, suddenly the problem becomes much more difficult. Like we don't have any good algorithms for this. Yeah?
It's kind of like the 3-body problem in
Is it like the 3-body and 2-body problem? Unfortunately, that 2 and 3 is not the same 2 and 3 here. But the point is that if we actually had an efficient algorithm to do this, then essentially that would break all cryptography. Right? All cryptography is based on the assumption that we don't have an efficient way of doing this. Like if we could do this efficiently, if someone had a way of doing it, they would break all existing cryptography. None of your information online would be safe. It assumes actually something even more than this. So what is really surprising and happens a lot in computer science and graph algorithms is that there's something that looks really easy and you can do it, and you change it a little bit and all of a sudden like it's hard. And we still don't have a good understanding of why that happens. It's a matter of research, but this is a real surprise. Now, why do things like tripartite come? So you could then think of like going further, right? What about breaking it into 5 parts? So you might say, why would someone want to do something like this? So one way this thing actually comes about is actually register allocation in compilers. So like when you write a piece of code, you have all these variables, right? But under the hood, there are only some registers. So often you want to reuse the registers as much as possible. What this edge says is these 2 variables cannot be used in the same register because they're occurring at the same time. So how do you assign variables to registers? Often ends up being something like this, some coloring problem. So if you have 32 registers and you've got, 1,000 variables, and you say that these 2 variables, they're actually occurring in separate parts of the program, so I can put them in the same register. So they won't conflict. A lot of those are actually coloring problems. So there are a lot of optimization problems, and we'll talk about some of them, which have this flavor of there's one version that's really easy, and you change something, and then suddenly we don't know if we can do it efficiently. Yeah?
So there's a efficient way of dividing things to 3. BFS can potentially crack precisely.
Yeah. I mean, we don't think that would happen, but yes, if indeed that was the case, people have tried. So, and there are reasons for why we know that this is difficult, but yeah. So we have just about 3 or 4 minutes left, so I don't want to start anything new. So I want to end any discussion on BFS with this lecture. Next lecture we'll start with depth first search, and so as you've seen, maybe if I've shown you that something that you thought you understood, like BFS has so many parts that are new, you'll see with depth first search it's even more so. Okay? So any questions, either about the homework or anything, this is a good time to ask. No? Okay, all right, so we'll end a few minutes early then.